good point. I'm presenting this paper here for a few people here. For Rob is the one who did like a lot of the work here. Bob, Luke, Dr. Buck in the audience here, and Dr. Anderson, who's got food poisoning right now. So, yeah. So, okay. I'll just jump right in here. So, the goal of this paper, or really the goal of what we were trying to do here, is we've got a micro UAV, a very small drone, and we're trying to basically come up with a method to estimate depth so that we can do real-time collision avoidance. So this is not going to be like the best structure for motion you can possibly get. I know like Dr. Powell does a lot of work with that sort of stuff. This is maybe a little more crude, but a little more real-time, a little more something you can do kind of on an embedded system. So the basic idea here is we can kind of divide what we're doing into 4 basic steps. So we start off with a video stream, and as the drone moves, we can kind of link frames that once the drone has moved a sufficient distance, then and hasn't rotated too much, then we can sort of consider those frames linked. Then we can try to estimate the camera motion. I've shown these are showing kind of SIF features, but we're actually using the onboard GPS and IMU kind of integrated with the compass to estimate the camera extrinsics. And then we use a method of epipolar warping to basically come up with row-aligned images, so that a feature in sort of corresponding rows will show up. So I'll get to that next. And then we use that to calculate the disparities, which then we can translate into depth using triangulation. So for the intrinsics here, we're going to be talking about both simulated and real world applications of this method here. And for the simulated method, we have the exact camera intrinsics, so we have everything that's needed to basically do the undo the lens distortions. In the real world case, you can kind of assume that we have a calibrated camera here, so we have the camera intrinsics, and we're able to basically remove all of the lens distortions, so that basically so that lines are actually lines. You know, they're not warped by the lensing effects. And on the right hand here, we're just showing basically a little visualization of some camera extrinsics, basically the orientation of the camera and the translation, the pose of it as it moves through like a little lawnmower collection here. On the left-hand side is maybe not the best image, but what we're showing is that we do image stabilization on the real platform. So we take the IMU and we try to, on the actual UAV, it kind of bounces around a little bit. So we do image stabilization so that the images are pretty similar in terms of their rotation. Okay, so jumping into how this method works, at the crux of it is this sort of thing called epipolar geometry. So in this case, you can imagine that you have a drone that is flying straight ahead and looking straight ahead. So you have kind of your 2 camera frames there, and their origins, if you imagine like a pinhole kind of camera with a little bit of a prism kind of shape where you've got like basically an origin, right? The line connecting those 2 origins is known as the epipolar line. And if you imagine a plane that is sort of rotated around that epipolar line, you'll get all the, or epipolar points, I guess, you'll get all of the epipolar lines. And what those are lines that are sort of corresponding between the images, right? So an epipolar line in one image and an epipolar line in the other image, the matched line, well, you'll see features that kind of line up, right? So that you can do this sort of disparity calculation. And the mathematics of it boils down to these 2 things called the essential matrix and the fundamental matrix. The essential matrix relates points in a normalized coordinate space. So basically like 0 is your center of your image, and I think like the edges is 1. The fundamental matrix is relating actual pixel coordinates to pixel coordinates, so you can actually kind of translate matching pixels. So a little more mathematics here. I won't go really too into it, but you can relate the fundamental matrix to the essential matrix using kind of these equations here, and may not be familiar with the little kind of subscript X notation. That's a way to take the translation vector and kind of write it in a skew symmetric way, so you can do this multiplication and kind of write out the essential matrix there. So if you do SVD decomposition on the fundamental matrix, then you're sort of getting the eigenvalues there. You can pull out the 2 epipoles for the 2 images there from the unitary matrices there, and those then correspond to your epipoles, right? So this is another example of kind of the visualization, sort of instead of going into the page, now we have two more of a traditional sort of stereo approach where you have two images that are a bit towed in, right? And then again, you have that plane that's being basically rotated about the line connecting the baseline that connects the origins. And what we do here is a bit of a rectification method. So this converts the images from being like X and Y, pixel coordinates to polar coordinates, or really we use the polar coordinates to then transform the image back into sort of a warped image here. So you can kind of see how we would do this if the epipole was a little bit outside the image there, and you can think about see where the lines kind of line up there, B to B and A to A, and you kind of going around the image and sampling it and then reconstructing it in this warped way. And the purpose of doing this is so that, like I said, so that when you have two corresponding pairs and you're looking at a row in one warped image and a row in the other warped image, that you will find matching features in that row. So you don't have to search the whole image, you just have to search rows. This might be a little bit of a better visualization for you guys to see, with a real image. So you take this kind of image of, I think it's like looking at a little house with some silos or something like that. And after we do the warping, right, what were sort of curves become straight lines. And if we have a pair of these, the rows will sort of match up so that we'll find corresponding points. So this is an example of that, where we have these two images. I believe this is forward motion, right? So going straight forward and looking straight ahead, not pointed in any direction. We have the two rectified images. And if you look, try to use the, let's see, oh. I don't want to use the red laser pointer. Let's point. So, so if you see, like we have, right, everywhere in the rows, we have everything lined up. So you should see, like this little bush is in the same row there. They're all kind of like aligned correctly. Gosh, there we go. All right. And then from that, we can calculate disparity. So we'll find a matching point in one image and the other image, and then we'll see how far apart column-wise they are, and that gives us a disparity, basically. So that's kind of the basic stereo, how that usually works. But by using rectified images, we can cover more cases than just the traditional, like your eyes, just traditional stereo. We can handle what if we moved a little forward, a little side, something like that. So we can compute a dense depth image by doing this block matching on basically every pixel, and then we can undo the rectification and get back a full dense depth image. The parts that are totally blue, I believe, or in this image totally red, are basically points that did not get matched well in our block matching. So those are, we're saying dense depth, but there are some parts where it just doesn't really work. This is just another example of moving forward, but looking down 45 degrees. So the camera's just pointed down a little 45, moving forward. This is on simulated data. Both of these kind of images are. This is of, we used AirSim actually, that I think Dr. Buck talked about a little bit in the talk a couple hours ago. And similar idea here. On the bottom left image is the produced depth image. We've kind of bended up in this case, so it actually does produce a smooth gradient, but we've just kind of bended up in I think like 10 or so different colors just for visualization purposes. And similar story there. This is just showing the block matching a little bit, just the idea behind it. We have a little kernel, like a little window, and we slide that along the row, and we basically just do a least squared error to try to find which one. And I think it's actually using OpenCV's block matching, so it tries to find which column basically in one image corresponds to the column in the other image for a given row, and does that for basically every pixel. So then like I said, we produce a disparity map doing that, and so this is highly parallelizable because basically each feature or each little key point, so to speak, can be done independently. And so we don't use actually the traditional disparity because we don't really have a traditional stereo rig necessarily. We have different scenarios, right? We have end of the page, we have little bit sideways. We don't have this fixed exact, basically offset between the cameras. So instead we do ray triangulation, where since we have the intrinsics and extrinsics of the cameras, we can basically project ray from one image out to the other one and see where they intersect, and then that gives us a rough estimate for depth there. So it's not perfect, but it's a pretty good estimate. So so this is just an example on the right-hand side of showing what does that point cloud actually look like if you were to take basically one of those depth images and then project it back into 3D space. And so you can more or less see the building there projected back out. And you do see sort of the sky has kind of poor block matching, and that's because there is basically like a little bit of a threshold, a little bit of a cutoff where it says, okay, if I didn't match well enough to any particular image. Also, there's sort of a symmetric block matching. So you say, okay, if I saw something that matched on the left image to the right image, did that same thing match on the right image to the left image? Because there should be that symmetry there where they should line up. So if it doesn't pass that check, then it basically throws out that point. And then here's just some examples of the thing actually running. This is, I'd say it's pretty much close to real time. It's kind of this GIF. I'm not sure if it's like exactly real time, but this is about what you can expect as it's running. So you have some examples of, I think the top are pure translation. Well, translation to the right on the top left. On the top right, we've got a translation just moving upwards. On the middle images there, I think they're both pointed 45 degrees below the horizontal and moving forward. And then on the bottom image, we have pointed straight ahead, moving forward. So, and you can see the similar kind of characteristics you see with the depth image, where sky is probably not the best. Sometimes you see with the lawn, maybe they're pretty similar features, but it does pick up the trees pretty well. And it's this kind of silo-looking object thing can kind of get pretty well. The car shows up pretty well in the simulated images, and even the little fence on the house or the supports, I guess. So that's, like I said, our goal is to take this micro UAV and be able to navigate in real time and do some collision avoidance. So the fact that we can kind of like do this real quick is pretty helpful for us. Now, this is I'm not sure if this actually made it into the paper, but this is kind of some interesting work that has recently been coming out that we're trying to look at. I know somebody asked a question back when Dr. Buck was presenting the AirSim stuff about, okay, how does this thing hold up to error, right? As you try to do these projections, it works great in the perfect sim world, but how does it work when you go back to the real world? And it looks like for translation error, it actually is relatively robust. We can add a random error up to, I would say, it looks like 10% still looks okay, 20% error starting to kind of not look so great. By the time we get to 30%, everything kind of starts to drop off. But 10% translation error is actually relatively significant when we're talking about half a meter or meter that you've traveled. So we don't really expect that much error usually from what we're getting. Now, the rotation error is where things are really picky, right? And this is kind of like this lever arm effect. So if you think about, you have like a really long stick, right? And if you just move it by 1 degree, at the end of that stick, it's moved like 10 or 15 feet or something, right? So you do have a lot of sensitivity here to rotation errors, and that's definitely something that we want to look at for future work, because you can see even with just, with about half a degree, things still look okay. But as you go to just 1 degree, 2 degrees of offset in the rotation there, things really start to break down. So it's kind of a common issue of structure for motion, but this is something that we're looking at, is probably doing better ways of refining our pose estimation to make sure that we have, or reprojecting that so that we have near identity rotation. Okay, so just kind of concluding with the future work here. So there's lots of little improvements to be done. I didn't really talk about all the specifics of what made this work, but the main novel part of this is that this is working real time. This is working producing dense depth estimates, and it's able to be done and handle a wide variety of different kind of camera poses and scenarios here as you translate and rotate. So things to be done to probably improve it is, you kind of saw in the real time is about 2 hertz or so is about how fast images are coming out. That's just a limitation of how we've matched frames. We basically say, okay, as long as we pick a frame if we move about a half meter forward, I think it is a half meter, as long as we moved at least a half meter, then we match the next frame. We would like to probably match way more frames than that, because there's probably lots more candidate frames that we could be matching and saying, okay, yeah, these are good enough to kind of create a pseudo stereo pair. So we could probably be cranking out, 10 to 100 times more, images or depth images per second or so. So, and then, yeah, just a few things with optimizing the search space and everything, making it run a little faster, a little better. But yeah, there's to conclude here, I've got a couple images. This is on the left. We have the simulated image. What we've done, we take the depth image and projected the color pixels back, and then on the then we did the same thing for the real world. So you can kind of see a little bit of idea of how well it's doing, and kind of what the drone, what we're able to see with our autonomy algorithms. So, and with that, that's pretty much all I have here. So I'll open it to questions.